So we're here at the example table, and in this video we're going to talk about integration by substitution. So let's remind ourselves of the chain rule. So the chain rule says that the derivative of f of g of x is f prime of g of x times g prime of x. Now, if we integrate both sides, we get f prime of g of x times g prime of x dx equals f of g of x plus c. And this is the basic idea behind integration by substitution. So let's look at an example. Suppose that we want to integrate 2x times sine of x squared dx. Now remember, what we're looking for is a function whose derivative is this thing on the inside, whose derivative is 2x sine of x squared. And just to note, when I say integration here, I'm using it fairly loosely, almost synonymous with antidifferentiation. So we're looking for a function whose derivative is this expression inside. Well, we already know the chain rule, and we know that the derivative of something like sine of x squared, well, if it is sine of x squared, we get cosine of x squared times the derivative of what's inside, which is 2x. And if we replace sine with cosine, so if we put cosine of x squared here, we know that the derivative of this is going to be negative sine of x squared times 2x. So if we throw a negative there, then we get 2x times sine of x squared. So just by looking at this thing, we can see that the antiderivative is negative cosine x squared plus c. But if we're dealing with something more complicated, then looking at it isn't always going to be enough. And even if we're looking at something this simple, we might want to be a little bit more explicit. So let's look at another example where we'll explicitly do a substitution. So now suppose we want to integrate 7x times sine of 5x squared. Well, similar pieces, right? We have an x squared thing inside the sign. We have an x outside the sign. But it's not quite as clear. We can't just look at this. Well, I can't just look at this by eye and know immediately what the answer is supposed to be. So we're going to do a substitution. And very often we use the letter u for our new variable that we're introducing. So we often call this u substitution. So let's make u equal to 5x squared. So in this sense, we're thinking of u as being g of x, the thing that's inside this function. So u is 5x squared. This means that du is 10x dx. So let's look up here. We have a dx and we have an x. We want to get something, we want to have in front of it a 7 instead of a 10. So let's multiply both sides of this expression by 7/10. So we get 7 over 10 du equals 7x dx. So we can rewrite this integral in terms of u. The 7x and the dx, so let's ignore this middle part. The 7x and the dx now become 7/10 du. And the sine of 5x squared becomes sine of u. So we have sine of u times 7/10 du. And this, well, we know the antiderivative of sine is negative cosine. So actually this needs a 7/10 out front, so let's make this negative 7/10 cosine u plus c. We have one more step because we want our answer in terms of x, not u. So let's make this negative 7/10 cosine of whatever u is in terms of x, and it's 5x squared. So that's how we can use integration by substitution. It's essentially, or you can think of it anyway, as almost the integration equivalent of the chain rule. Let's look at another example. So this time, let's compute a definite integral. So let's look at the integral from 5 to 11 of e to the 1 over x all over x squared dx. So we have to figure out what kind of substitution to do here to simplify this expression. And what we're looking for is something inside another function, right? We're thinking in terms of something like f of g of x. So we're looking in here for a g of x. Now we have e raised to a power that's not just x. So in this case, 1 over x is a good candidate. The worst that happens if we try it, we're wrong. But let's think about it. So if 1 over x is g of x, the derivative is almost 1 over x squared. So if we rewrite this as the integral from 5 to 11 of e to the 1 over x times 1 over x squared, then it might become a little clearer. So here we have f of g of x, and here we have our g of x. Actually, this is not quite f of g of x, but g of x is our 1 over x is our candidate for g of x. So let's say u equals 1 over x, and then du is, well, again, it's not quite 1 over x squared, but almost. It's negative 1 over x squared dx. So if we want to replace 1 over x squared dx, we move the negative to the other side, and we get negative du equals 1 over x squared dx. So let's rewrite this thing in terms of u. So we get e to the u, and 1 over x squared dx becomes negative du. So let's put the negative on the outside and just write du. But I've forgotten one thing. I haven't written the limits of integration. And this is a very key point, something that you don't want to forget. These limits of integration are in terms of x. We now have an expression in terms of u. So you have one of two choices. You can either rewrite the limits 5 and 11 using this expression, or you can write x equals 5 and x equals 11 as your limits. So in this case, I think I'll just write them in terms of u, because if x is 5, then u is 1/5. And if x is 11, similarly, u is 1 over 11. But we can also think of this as being x equals 5, and this thing up here as being x equals 11. Now, if you do the substitution so you have 1/5 and 1 over 11th, you can carry out the rest of the problem as if u were the variable you started with. Otherwise, you'd have to integrate and then substitute back in for x. So let's keep going. We now have, well, we know what the antiderivative of e to the u is. It's just e to the u. So we get negative e to the u, and this is evaluated between 1/5 and 1/11th. So this becomes negative e to the 1/11th minus negative e to the 1/5, but the two minuses cancel, so we get plus e to the 1/5. So this is our answer.